Hello, and welcome to another one of Ethan's engineering videos. Today we're going to be working on our comp methods homework number 2, part 6, I believe. Again, the numbering scheme we were given was a part 1, part 2 with an A, B, and C, and then an A, B, C, and D. But that's too complicated for me. I don't like that, so I'm just doing 2.1 through 2.7. But this is 2.6, and today we're going to be working on Broyden's method of finding the roots of a function. So if you remember previously, we did a secant function. This is the function we were using right here, func of x. This is what it looked like. We used the secant method to find the roots of the function, given 2 points on that function. Then we came up with a Newton method, which just used the derivative in a single point. And then we updated that to use matrices with Newton matrix. So today we're going to be taking a look at Broyden's method, and specifically with Broyden's method, how to cut out more of the inefficiencies of Newton's method with the matrix. So let's get right into it. So basically the goal of Broyden's method is to cut out the inefficiencies that are involved with, let me make sure, this step right here. This is the step that eats up a lot of processing power because taking the linear algebra inverse of a matrix is computationally expensive. So we want to minimize doing that operation as much as possible. So Broyden's method, I have the Wikipedia page pulled up right here, essentially solves that problem. He was a very, very smart man who essentially figured out that if you, and again, all of this is like, I proved this in the following video, 2.7, but this is 2.6, so we don't have to worry about it. All we have to know is that this right here that I just highlighted is the way to update a Jacobian based off a previous Jacobian. So we can make an iterative refinement of a Jacobian with a new Jacobian, and that way we don't have to calculate the actual Jacobian of a function each time. We can just improve our assumptions over and over again and slowly approach the actual Jacobian while also using way less computational resources. For the purpose of what we're going to be doing today in Python, we're going to be actually using this version of his formula, which instead of updating the Jacobian itself, we're going to be updating the inverse of the Jacobian. This uses the Sherman Morrison formula, which if I pull that up, it's a lot of complicated matrix stuff. It has to do with the identity matrix and easy ways to, and this proves that it's computationally simple to update an inverse of a matrix. And then this right here just tells us how to do that in accordance with like the terms we're going to be working with, delta x, delta f, and the old inverse of our Jacobian. So I'm just going to have this here to reference, just to directly plug it into our thing, because we're going to prove that this right here, no, that's what we're going to be using. I circled the wrong one for a second. This is a less good version of this. So this is what we're going to be using in this video. This is what I'm going to prove is true in the following video, which I've already completed ahead of time because I felt like getting the conceptual basis down before doing this one would be well. But going from here to here is just kind of changing terms and doing some algebraic rearrangement. So it's leave it as an exercise to the watcher of this video. So anyway, this is what we're going to be going with. So we're gonna come back to this when we actually get to writing our code, which we're going to start now. And so to start, I'm going to just be getting rid of some of this stuff from our previous video and pasting this in here. And so our Newton matrix, we are going to rename this. I'm just going to call it Broyden, but all of this input is going to stay the same. And now we can actually start coding up Broyden's method. So the first thing you're going to notice is that, again, we're not just inverting the Jacobian each time. We're going to be innovating and iterating through the inverse of our Jacobian. So the first thing we're going to want to do is we're going to want to rework the stuff in here, but we need to take the inverse of our Jacobian first. So the first time we run this, we're going to have to calculate the inverse of our Jacobian. So we're going to do this, and we're going to call this JINV. So this is the true, honest to goodness inverse of our Jacobian right here. We take the Jacobian of our function, which I'm going to take f Jacob, and I'm probably just going to call it, yeah, that's fine. It's fine enough, Jacob. So here now we have our inverse of our function, so we can actually start iteratively improving this inverse to solve for our root right here. So what we're going to do for each of our range, I'm going to try to space this out a bit more so we have a bit more room, just so I can see, because we're going to be inserting stuff into this function, because our Newton matrix works great for the Newton method, but the Broyden's method obviously is significantly different. I'm going to get rid of this if-else, because there's going to be some extra logic in there that we're going to have to deal with, so I'll scoot that away. But this is true. We still want it to stop breaking if we're close enough to our tolerance, so that's fine. So as for this right here, you can see the technique we're going to be using. It works with our delta x of n and our delta f of n, so we're going to have to calculate those. So the first thing we're going to do is we're going to define our delta x. I'm going to say dx is just going to be equal to this right here. So I'm going to literally copy and paste this. Obviously, we don't need to have this because we've already defined that up above. That's our J inverse. So our dx is going to be our inverse Jacobian times f of 0, and then we're just going to add dx to x0 to get x1. So that's our really simple first three steps. It's pretty much the same thing as the methods. We just redefine some terms to make the later work a bit easier. So where do we go from here? Well, we're going to do the same thing. We're going to check to see if our f1 is within our tolerances. If it is, then we can just break out and say, yep, that was a good enough step. That took us basically right to 0. Set them equal and return. But if they're not, we have to obviously do our iterative improvement, because we can't just, like what we did up here, just keep iterating through this as it is. We have to actually improve our Jacobian without taking the inverse over and over again. So how are we going to do that? Well, again, that's where Broyden's method comes in. So we're going to essentially put all of this in here. So our new inverse of our Jacobian is going to be equal to our old inverse times this fraction right here with these two terms on top. So we're just going to put that in. So J inverse is going to be equal to our old J inverse plus, and then that's where this fraction is going to go. So we have on the top, we have delta x minus Jn minus 1 times delta f. We also have to define delta f. So what exactly is delta f? df is going to be equal to f1 minus space minus f0. So that's obviously the difference between the outputs of our two inputs, right? So we solved for, we have our x0 and our f1, right? We have our x0 and our f0, then down here we calculate our x1 and our f1. We've made sure that it's not quite close enough to be considered our final answer, so we have to calculate a df and then improve our matrix. So we have on the top of this fraction is going to be dx minus J inverse matrix multiplied by, because again we're working with matrices, times delta f right there, and there's no transposes up there. And then we're just going to do this other matrix multiplication because it's fairly easy. So that's going to be matrix multiplied with this right here in parentheses, which is going to be dx dot transpose. I believe capital T is dot transpose. Dx, yep, dot transpose, matrix multiplied by the inverse of our Jacobian, J-I-N-V. And then this whole thing, which I'm going to wrap in parentheses just to make sure it's completely covered. Oh, put spaces there so it's still legible. Is going to be multiplied by our denominator. And our denominator is just going to be these three things, matrix multiplied together. So parentheses, I think it was delta x transposed, delta x dot transpose, matrix multiplied by the inverse of our Jacobian, J-I-N-V, matrix multiplied by the delta f, and that was not transposed, correct? Yes. So this is essentially right here is kind of the big discovery of Broyden is again this right here, which I'm going to prove in a separate video. In fact, I might just slide that image right in right there of our finished work, since I've already completed that video. Even though it's later in our series, we'll do a little blast from the future, back to the future type stuff of that we proved it with a whole big chalkboard. And then this is just an algebraic rearrangement that is going to incorporate the inverse of our Jacobian instead of iteratively improving our regular Jacobian. Got a notification about an email that I'm going to get rid of really quickly, but this is like the big. This is the meat of the change, meat of the Broyden. So that's what's really important here. So again, if this didn't work, we have our new inverse. We update our old x0 and x1s, and more or less we're good to go. Unfortunately, if you were to run this, you'd run into a bunch of issues and it wouldn't actually function properly. And we would have to go through a whole bunch of diagnostic testing to figure out why that was the case. But the short answer is because we're using an approximate Jacobian, right? Just like up here, we had to account for tolerances because that's a pretty big assumption that everything's going to work linearly. There's also an assumption we're making here that when we figure out what dx is, right, our inverse tells us this is how much you should move to go to 0, and you take that step of dx, it's possible you can overshoot, and when you do that, everything will kind of fall apart. Or if you're relatively close, it might also start going into rounding errors, and you'll start having issues just because of the way that numbers store bits in binary. So our way around this is going to be using something called an alpha value to reduce our step size. In our homework, we're required to talk about using a step size adjustment. So that's what this step is going to be. So we're going to create our new step size variable, which I'm going to call alpha. And that's just going to be equal to 1. So why does alpha matter? Because we're going to check to make sure that we're actually going in the correct direction, right? So in this case, we checked here to see if our final answer was close enough to 0. But what we should do before we check for that is to make sure that we're going in the right direction, that our dx isn't misleading us. So if our dx has gotten corrupted by either round-off errors or some other unknown issue, we should check to make sure that we're actually going towards 0 instead of away. So how can we do that? Well, we can say, and we can use while, actually would be better. So while jnp dot linalg dot norm. So while the normal of f1 is greater than the jnp linalg norm of f0, so what this is saying is when f1, the value we just solved for, is farther away from 0 than our original number, which is obviously bad, that means we're going in the wrong direction, we're going to want to adjust our dx so that way we don't overshoot. Because if this is at like 3, and this says, yeah, go -5, or it says go -10, and now we're at -8. Obviously, we're farther away from 0 than we were before. We've overshot. So that negative 10 needs to be scaled back so that we actually end up at 0 instead of going way past it into the negatives. That's my really, really simple number line example. So while we overstep our boundaries, we want to change our alpha to be equal to the current alpha, ALPHA, times, we'll use, for example, 0.75. So that would say, okay, so instead of moving by a whole -10, only move by 3/4 of that, so only move by -7.5. And if you check that, that's obviously still going to be farther away. So how do we check that again? Well, we just are going to recalculate our, our dx isn't changing, but we are going to want to calculate these right here, our x1 and our f1, but instead of just using this directly, we're going to multiply it by our alpha value first. So that way we're reducing the size of our alpha before we're calculating our x1, and then we can calculate our new f1. And this right here should tell us hey, so again, reduce your step size so that f1 doesn't overshoot 0 and actually become farther away and then start kind of bouncing back and forth and way overreacting, and again, it will spiral out to infinity and fall apart. This is one of our pretty simple constraints to make sure that we can modulate how much we're moving by each time so that we don't overstep 0 and start spiraling out of control. The other thing we want to do is say, what if we get caught in this while loop? Not by some kind of coding error, but for example, we're going to a place that's so corrupted that even reducing the step size doesn't help. So, for example, if our step size was just infinity, right, and no matter how many times you multiply that by 0.75, that reduce the alpha factor, it's still going to be some absurdly large number, and it's not going to work. So what would happen then is we would just be caught in this while loop where f1 is never lesser than or equal to f0, and so we're making no progress, and we'd just be stuck here. So we also have a secondary solution, which is to look at our actual alpha and say, if our alpha gets way too small, because again, each time this while loop iterates, our alpha is shrinking. If our alpha gets too small, we should just abandon trying to save computer resources, say we've reached a dead end, and recalculate our J inverse at our new x0. So we're just going to scrap all of this iterative stuff we've done right here, and we're just going to say okay, I apologize, we can't save computer resources here. We've reached a dead end of improving our inverse Jacobian. Let's just start over. So we're going to do that with an if check. So we're going to say if alpha becomes less than, and then we're just going to put some number in. I'm going to just say 1e to the -8, because I think that's a pretty decent number. Well, what are we going to want to do? Well, we're going to want to abandon ship. So what we're going to do is we're going to recalculate our J inverse. So we have our upgraded J inverse now, and then we're going to want to recalculate our d of x. Oh, I didn't want to cut that. I wanted to copy that. So again, what this does is it says hey, we've reached a dead end. Our alpha is so small that we're basically not taking any steps anymore, right? Our next step is not moving. So it thinks that we've reached a minimum, right? So it thinks that there's no way to get our F1 closer to F0. It's just impossible. So what we're going to do is we're going to take the Jacobian at that point to kind of recenter ourselves, spending more computational resources, yes, but gaining perfect accuracy because it's the actual Jacobian. And so hopefully that will get us out of any potential binds. So I'm pretty sure, just double checking, that's everything we need to do. I can make this a bit closer together because, again, all this is doing it. This is calculating our x1 and our f1. This is going to confirm that our x1 and our f1 are what they're supposed to be. And then, I should recalculate dx because our dx up here that we're using in this formula right now, I just realized that's a mistake. This dx is either going to be made from our initial guess, which could be correct, or it could be from down here. But you'll notice that our dx is only going to be redefined if we get the alpha trigger, if this if statement is triggered. However, if we reiterate this a million times, it won't work. So what we're going to do right here is just add in a quick little dx is going to be equal to, because the dx isn't needed to calculate f1 and f0, since we've already calculated, dx is going to be equal to x1 minus x0. The other thing we could do is we could put that down here, but I feel like that wastes a little bit of space. I'd rather just oh no, wait, because we need our dx to be kept the same, because again, right here we're iterating through alpha, so we can't do that here. Okay, so I guess we do have to put it down here. So we're going to do df comma dx is going to be equal to, and then dx is just going to be x1 minus x0. So yeah, if we were to change our dx in here, then our alpha value would kind of, because again, right here we're adjusting the alpha, the multiplicative factor of dx, so we can't change dx or else it would kind of defeat the purpose. So we need to make sure that we're recalculating dx outside of, or after this while loop is confirmed that we are doing a significant step that's not overshooting and may need to be corrected, and also we're not at our final answer. But now I think that now that our dx is correctly defined, everything else here is correctly defined. I'm going to do a quick double check to make sure that this actually works the way I expect it to. I want to make sure that I'm not doing it backwards. So if I say this is 5 minus 3, and this one is 5 minus 1, or if I do 5 minus 4. Oh, I hadn't apparently connected to runtime this entire time. That's a little silly of me. It's connecting now. So I apologize for the probably 2 or 3 seconds that it's going to... hopefully my internet is connected. Initializing, there we go. Okay, there we go. So if I check my variables real quick, I should say df is a value of 2, correct, and dx is a value of 1. So yes, it is in order. So this is the first one, this is the first one. Those two do line up. Now that I've realized that I forgot to initialize this, I should probably import all of the numpy, jax, scipy that we need, import our function, or define it at least. Leave that up, and then also get function 2 defined, because I want to test it with both of them. And now hopefully this should, okay, so it said there's no syntax errors, so that's good. And let's test if this works. So again, from what we know before, I'm just gonna run these ones as well, so I can double check. So again, the secant of our regular function gave us negative 0.8 essentially, and the same thing with Newton here, it gave us also negative 0.8. So let's try that with this one right here. So we're going to try Broyden, and we're going to put in our function right here, func, and we're going to put in our x0, which is going to be what was the x0 we used for all of these. Looks like negative 0.44. We'll try negative 0.44. Hopefully it spits out negative 0.8. That's a good sign. So the other one we can check from this function would be, I think it was, that was a negative 0.44 when we just did. That's negative 0.2, is it? But there's negative 0.8, so negative 0.2. So if we pick 0, that should work. hopefully 0 dot parentheses 0.2, and that's within our tolerance. Our tolerance is e to the negative 12. That's good. So that's proving it's working with our simple function that's just taking in a scalar and returning a scalar. So now let's try it with our func2, which is up here. I probably shouldn't have deleted my those two checks, the two checks we had down here. I wonder if I can bring those back. Control MZ. Control MZ. Oh, that's not what I want to do. Okay, well, there we go. We'll bring that back. Yeah, it didn't bring back what I wanted, but it's whatever. Okay, well, I guess our previous checks are gone, and I don't really remember what these two are. So I guess I'll rewrite those real quick. Darn, I should have just kept going. I should have gotten rid of those. Newton matrix at func2, and I wrote it so that I could take in at least 1, and I think I did 0, 0. I guess we'll just do all zeros. There's three inputs it's expecting. So we know Newton matrix works, or it doesn't, apparently. I feel a little silly. Oh, you can't have 0 because of the square root, correct. So we'll just do 1s, I guess. And I really wish I had deleted those. Okay, that's within our tolerances. There we go. Negative 0.8, that's definitely one of them. Negative 1.6 and 4.9. So that's what we're getting at here. We know this works. Again, we proved that in our previous video. So let's copy this and then change it to Broyden, and hopefully we'll get the same more or less answer. Broyden. So not quite.
A lot of boring math later.
After looking through my own work and being totally unable to figure out what was wrong, because objectively it is not wrong, I just realized it's because my guess was bad. I wasn't sure what to do because it worked over here, but that's just because this function works totally differently from this one. All I had to do was, if I increased this from 111, you can see that there's many full wipes, and we only get to about negative 0.8 accuracy before we run out of tolerance, max iter. So what I'm going to do is, for this one, I'm going to say max iter, there you go, is going to be equal to 100. And it might actually reach the, no, it still doesn't. Okay, well, that's fine. I think it's basically because my guess is bad. So if I go stick with the stock iter and I move it up to 3, because again, if you look at this, you can see that in this one that did work with our 111 and it had very high accuracy. It was looking at negative 6 and 4.9, so almost 5. So if I just bump this up to 3, you can see we only do 4 full wipes, and then we found the actual correct answers right there. So I think what this tells us is that the Newtonian matrix method, again, is more computationally intensive, and it will always be going in the correct direction. And Broyden's method does function, and it does save computer resources. As you can see, we only had to calculate the inverse 4 extra times, excepting the one that was mandatory. And you'll notice that we saved a lot of computer resources by doing that, but we were significantly more dependent on our guess. If I were to do 2, I think we're going to have a couple more full wipes. We get total garbage, but at 3, it works almost exactly as expected. So I think Broyden's method is a lot more sensitive to initial guesses because of all the assumptions we're making about our inverse and skipping calculating our inverse on every term. And it's a bit more finicky and a lot more touchy. But I've triple checked all of my work, and it is correct. I think first of all, these functions that I created up here are very complicated and not very easy to model when by using the linear approximation that we do, because we assume that we can approximate it with our inverse. And I think this one is just a bit more stable, although more computationally expensive, because it always goes the correct direction. This one is computationally cheap, but we take shortcuts, and those shortcuts can lead us to spiral out of control. But yes, so it does in fact work. It's just very, very sensitive depending on our guesses. We have to have good guesses in order to make this work. But with that out of the way, figuring out that little hitch, again, I don't really want to re-record the whole 30-minute video when all of my work was correct. It was just me not putting in a correct guess because I wasn't sure exactly how to guess correctly without looking at some of the previous work we did. But again, sometimes the fault is you and not on the code you've written. So make sure you're double checking your own thought process as well as your own code and your own work. But despite all of that, I thank you for watching. I appreciate your time, and have a good evening.